Hello there, welcome to this video, which is the continuation in our mini-series on the elevation factor. My name is Tom Meyer, and this is a production of the American Association for Geodetic Surveying. In this video, we are now at a position where we can explore the various radii of curvature that we use in Geodesy, and in particular, we're going to focus, of course, on the ones that we use to compute the elevation factor. Here's our notation. As we saw in the previous video, we'll use an italics Roman letter A for the length of the semi-major axis in meters. E squared is the first eccentricity squared, and C is geodetic latitude in radians. The first radius of curvature we're interested in is called the meridional radius of curvature, or the radius of curvature in the meridian. This is the radius of curvature that runs north and south. The formula, you see it there on the screen. So let's get a feeling for what this radius of curvature means. In our picture here, we see an ellipse. This ellipse is, you could think of it as a reference ellipsoid in profile, or probably more specifically, this is a meridian. All the meridians are identical, so pick your favorite one. Here's a meridian. Now, at the equator, we see that the ellipse, the turning of the ellipse is tighter at the equator than it is at the poles. So from our video on curvature and radius of curvature themselves, we know that when the curve is tight, this leads to a smaller radius of curvature, and when the curve is gentle, this leads to a larger radius of curvature. This is going to lead to the unintuitive situation that the radius of curvature in the meridian at the equator is smaller than the radius of curvature in the meridian at the poles. That seems backwards, right? But it's true, and you can see it in the picture. Let's actually compute these values at the equator and at the poles. Let's see what the numbers actually work out to be. So let's go for the equator first. So phi is equal to 0. If I plug phi of 0 into our formula, I have the sine of 0, which is 0, and the eccentricity squared times 0 is likewise 0. So I have 1 minus 0 is 1, 1 to the 3/2 power is still 1, and so it works out to be A times the quantity 1 minus the eccentricity squared. Well, the eccentricity is a small positive number, so 1 minus that is a number that's just a little bit less than 1. So clearly M sub 0 is going to be less than A, because A is being multiplied by a number that is a little bit less than 1. So not only is the radius of curvature in the meridian less than A at the equator, it's actually even less than B. It's less than the length of the semi-minor axis, and I have shown you the value for the semi-minor axis here, and I've colored in red the first digit where these two numbers are different, and we see that it's different. It's 56 kilometers versus 35 kilometers, so it's different by tens of kilometers, almost 20 kilometers shorter than B. That's just the way it works out. Okay, well, what about at the poles? We know it's going to be a bigger number at the poles. Our argument from the previous slide leads us to anticipate that. So when we work this out, so the sine of 90 degrees is 1. So we have 1 minus eccentricity squared to the 3/2 power. The 3 cancels, and it leaves me all of this stuff. There's some algebra to do, and it leaves us with A over the square root of 1 minus the eccentricity squared. This number is larger than the semi-major axis. You might recall the semi-major axis is 6,378,137. And again, I've highlighted in red, I've colored in red, the first digit where these numbers are different. So this is basically 78 kilometers. This one is essentially 100. Again, we're different by tens of kilometers. Now, considering that the number itself is in thousands of kilometers, it's not a huge difference, but nonetheless, I think it's a little bit surprising, but that's the way it works out. Now, for the east-west radius of curvature, This one has a really fancy name. It's called the radius of curvature in the prime vertical, and the formula, you see it there on the screen. The first thing I'd like to point out about this, despite the fact that this radius of curvature is an east-west radius of curvature, it is not the radius of curvature of any of the parallels with the exception of the equator. So hearkening back, do we hearken back? Yes, let's hearken back to the video on curvature, and we know that our radii of curvature are perpendicular to the curve at the point of tangent C. So if that's true, that is true. If we look over here at the green line over here on the right, at the point of tangency at this point right here, you'll see that the direction that is perpendicular to the surface of the ellipsoid runs in the direction as shown. And this is not the radius of curvature of a parallel. A parallel at this point would be perpendicular to the purple axis, the z-axis. And so this clearly is not the radius of curvature of any of the parallels. Furthermore, let's suppose that it was. Well, the radius of curvature of the equator is equal to a, that's fine. But as we go further and further polewards away from the equator, well, the parallels are becoming smaller and smaller and smaller until, in fact, we get to the pole itself. And a degenerate parallel at the pole itself has a zero radius. This is not what we're interested in. These radii are supposed to be reflective of the radius of the Earth at that point. So hopefully it's clear. We cannot use the radius of curvature of any of the parallels. This is a different thing entirely. I'm not going to show you where this comes from. I'll ask you to consult a book on geometric geodesy to see where it comes from. We don't need to go through that here. But I do want to dispel any confusion that might arise that in here is equal to the radius of any of the parallels. So why in? Well, in the previous slide, we have m is the radius of curvature in the meridian, and m is for meridian, I suppose. And this is the next one, so we decided to name it n. That's not the best name, perhaps, but it is a name, so we'll just go with it. Another interesting property of the radius of curvature in the prime vertical is that value, that radius of curvature, is the distance from the z-axis, from the minor axis, to the surface of our reference ellipsoid. That quantity is useful in geometric geodesy. We need to know that number for various things from time to time. We won't need to know that we won't be using the radius of curvature in the prime vertical in that particular way when we're talking about the elevation factor, but it's a useful fact to know it. No, that it comes up in the conversation from time to time. Also, notice that I have denoted this angle as phi. This is, in fact, geodetic latitude. Notice that geodetic latitude, the line that we're using off of the equator, that geodetic latitude is subtending here, notice that that line doesn't go through the center of the ellipse. Anytime a geodesist draws latitude, they go out of their way to show that that line doesn't go through the center, but it's going to intercept the ellipse's minor axis somewhere below the center down here. And this is the reason. It's because this line is perpendicular to the ellipsoid. If it came out from the center, it would not emerge perpendicularly to the ellipsoid. And so we go out of our way to show that this is geodetic latitude. I'd also like to point out that the same argument is exactly true for the radius of curvature in the meridian. The radii of curvature of the meridian are just as perpendicular to the surface of the ellipsoid as the radius of curvature in the prime vertical. They have to. All radii of curvature are perpendicular to the curve that they are defined on. And so it's not that this is special. It's not that the radius of curvature in the prime vertical is special in this way. It's just this is the way we normally draw this picture. Latitude is usually drawn as the angle between the equator and some other line that goes through the point that we're interested in. And it's more evocative to do it with the radius of curvature in the prime vertical than to do it with the radius of curvature in the meridian. Okay, so now let's compute some radius of curvatures in the prime vertical. Again, let's start with the equator. So phi goes to 0. Well, the sign of 0 is 0, and so the denominator just turns into 1. And we see that the radius of curvature in the prime vertical at the equator is equal to the length of the semi-major axis. That's completely consistent with the intuition that we were developing here, that the radius of curvature in the prime vertical is the distance from the ellipsoid to the minor axis. Well, at the equator, that has to be the semi-major axis. Well, what happens as we go northwards from there? Let's take a look at the poles. Well, at the poles, we're taking the sine squared of 90 degrees. This ends up being a divided by the square root of 1 minus the eccentricity squared. And you might remember from a few slides ago, this is exactly the same value that we got from the radius of curvature in the meridian. This is the meridional radius of curvature as well. And so this number, it's not only greater than B, it's greater than A. Both of these radii of curvature, at least I think it's surprising that they are both greater than A at the poles. I think it's also very worth thinking about why is the radius of curvature in the meridian equal to the radius of curvature in the prime vertical at the poles. I'm going to leave that as an interesting thought experiment for you to ponder yourself. Why are those the same? So I've worked out the values for m and n at various latitudes, so there's a whole bunch of numbers. Okay, but the final column is the difference between n and m, and we see that at the equator, n is greater than m by almost 43 kilometers, and then of course the number drops until there's 0 at the poles. We already know that they were 0 at the poles. This little table gives you some idea of the difference between the two. Well, tables are fine. Let's look at a plot. The orange line, the orange line, as we know, is radius of curvature in the prime vertical, and it starts out at A, and then it increases until it gets to the highest value that it achieves at the poles. The blue line down below is the radius of curvature in the meridian. We know that at the equator it's less than B, and it achieves the value of B here at, 33 degrees, something like that. It achieves the value of A at about 55, just coincidentally. I don't think there's anything magical about these two latitudes. It's just the place where the radius of curvature in the meridian happens to equal the length of the semi-major and the semi-minor axes. And then eventually it equals the radius of curvature in the prime vertical up here at the poles. Stepping back for a second, what we're trying to do is compute an elevation factor. That's the goal. And we need this value of R. R, as we know, is a value that represents the radius of our reference ellipsoid at the latitude in which we're working. Well, at this point, we see we've got two values for radii of curvature, namely M and N. Well, there's two of them. Which one should we use? The answer is neither, generally. What we need is a single number, and upon reflection, we know that, so we're thinking about reducing a distance corresponding to some line on the ground. Well, that line is running at some geodetic azimuth. So perhaps it seems like what we really want is the radius of curvature at that latitude, but it's running in the direction of the azimuth of the line. M runs north and south. N runs east and west. Let's figure out what the radius of curvature is in the direction that the line is actually running. That is called the radius of curvature in the normal section, and it's got this somewhat complicated formula that you see here. So computing the radius of curvature in the normal section, it's entirely doable. We could certainly do this, but it's a little bit inconvenient because it requires us to know the geodetic azimuth of the line that we're measuring, and that information might be somewhere between inconvenient and actually problematic to come up with at the time we need to do this reduction. It sort of assumes that we already know the coordinates of the forward point so that we can calculate that azimuth. We've got horizontal angles coming out of our total stations, but unless we've gone through the traversing process and converted those horizontal angles into azimuths, probably what we actually have coming out of the data collector is an azimuth, is a direction relative to the backside. And so knowing the azimuth of this line might not be super convenient. So it turns out that it's going to work out just fine if we use the mean of our two radii of curvature, M and N, instead of going through all of the monkey puzzle necessary to calculate the radius of curvature in the normal section. There's more than one kind of mean, and the one that matches our theory the best is a thing called the Gaussian radius of curvature. It is a geometric mean as opposed to an arithmetic mean. It's the product of M and N, and that quantity square rooted. So it's going to have the correct units. M times N both have meter. Each one of those has meters, so the product is meter squared. Then we take the square root and we end up back with meters. Looking at the plot over on the right, the Gaussian radius of curvature is the green line right in the middle between the other two radii of curvature, as it must be. It is a mean value. So this is the one that we use for the state plane coordinate system of 2022. It is not going to be the value that we use for state plane 83, and that's the one we use for the modern state plane 22. So now you might be wondering, well, how different is the geometric mean from the arithmetic mean? And the answer is not very different at all. The most different they are is at the equator, and they're only some 36 meters different at the equator. So we could use the arithmetic mean, and it would not make any practical difference. But as I said, the Gaussian radius of curvature is theoretically more correct than using the arithmetic mean. And so that's the one that we're going to use for R in our formula for state plane 22. Okay, so now we know how to get the value of R. In the next video, we'll actually compute some elevation factors. See you then.